with sequences and series. So on this screen here you'll see that we have the definitions of an infinite sequence and a finite sequence. First of all, a sequence is an ordered list of numbers like 1, 2, 3, 4, 5, 6, 7, 8, or 2, 4, 6, 8, 10, 12, something like that. Okay? Each number in that list is called a term, and there are two types of sequences. Like I said, we have infinite sequence, and infinite means, of course, it goes on forever, never ends, and that's what you can see here, that it shows a sub 1, a sub 2, a sub 3, just meaning the first term, the second term, the third term, goes all the way to like the nth term, and it keeps on going forever. But a finite, there's between infinite and finite, the finite stops at some point. Okay, it's only the set of only the first n terms of the sequence, meaning, you know, it's a1, a2, a3, all the way up to a sub whatever it is. Like if I was trying to find the first 10 terms, that'd be a sub 10. Okay, so let's look at some examples here. We have, it says write the first 5 terms of the sequences given by, so let's look at part A here. A sub n is equal to 4n plus 3. And that, all that means is we're going to take 1, that's the one we're starting with, we're going to plug in 1 for n. So it'd be 4 times 1 plus 3, which of course is 7. Then we plug in 2, so 4 times 2 plus 3 is 8 and 11. And then 4 times 3 plus 3, that's 12 and 15. And then 4 times 4 plus 3, which of course would give us 19. Okay, that's all. It's kind of simple there. Just plug in the value in for n and figuring out what the sequence is, what the sequence is going to be. There's 7, 11, 15, 19, so on and so on. Okay, part B says a sub n is equal to 2 plus a negative 1 to the n power. So here it gets a little bit tricky with the signs. It's really important that if you put a negative 1 in the calculator, if you're doing that on your calculator, you put negative 1 in parentheses, because the negative is being taken to that power. A negative 1 to the first power is just a negative 1. Plus 2 is 1. 2 plus a negative 1 squared. A negative 1 squared would be a positive 1. Plus 2 is 3. 2 to the negative 1 to the third power would be a negative 1 plus 2 goes back to 1. And 2 to the negative 1 to the fourth power would give us a positive 1 plus 2, of course, is 3. Okay. And then we look at the part C. Negative 2, a little bit more complicated one. Here's with a fraction, so we plug in, again, starts with 1. And negative 2 to the first power over 3 times 1 minus 1, and negative 2 to the first is just a negative 2. 3 minus 1 is 2, so that just goes to a negative 1. Plug in 2, that would be a negative 2 squared over 3 times 2 minus 1, and negative 2 squared is 4. 6 minus 1 is 5. And of course we can't reduce that any further. And then we have a negative 2 cubed over 3 times 3 minus 1. That is negative 2 times negative 2 is 4 times negative 2 is a negative 8. 9 minus 1 is 8, and that goes back down to a negative 1. And then we have a negative 2 to the fourth over 3 times 4 minus 1. This number up here on top would be 16, and 12 minus 1 is 11. So there's my pattern there: negative 1, negative 4 fifths, negative 1, 16 elevenths. So you see some of the patterns are easy, just add 4, goes alternate 1 3 1 3, but this pattern over here doesn't look to be much of a pattern. Okay, so let's move on to example number 2. Okay, so now we're going to look at example number 2, and it says write the expression for a parent nth term a sub n of each sequence. And what this is doing, this is saying, kind of going backwards from what we did before. Last time we gave you the expression and you had to tell me the terms. Now we're telling me the terms and you got to figure out what the expression is going to be. Okay, so the way I always start these off by is making a little chart like this. Okay, where n is the number of terms, so that just simply means, you know, the first term, second term, third term, fourth term, so on, so on, so on, all the way to get to my n. Okay, and all I'm doing here is writing 3, 5, 7, 9 because that's the terms that they gave me, and I got to figure out what this equation, what this expression is over here. If I try to just look at this right now, if I try to get from 1 to 3, 2 to 5, 3 to 7, I've got to be able to do the same thing every time. I add 2, I add 3, I add 4, I add 5. So obviously that is not going to work. Okay, so what I do is add another row to my little chart here, and we got to think about multiplying by 2, by 3, by 4, by 5, or squaring it, cubing it, or multiplying by -1, doing a lot of different things that we can do to this n to try to see how we can get to our terms that we're looking at. So let's just start off by looking at 2n. 1 times 2 is 2, times 2 is 4, 3 times 2 is 6, 8, so on, so on, so on, and that is really 2n. Okay, now if I compare 2 to 3, 4 to 5, 6 to 7, 8 to 9, I am adding 1 every single time to those, aren't I, to get to those. So my formula is going to be 2n plus 1 would be my a sub n. I'm going to look at part B for example number 2. Same thing again, and I just want to find the sequence for the expression for the sequence 0, -3, 8, -15. So what we're going to do first is just look at the number. Ignore the sign right now. Let's just look at the 0, 3, 8, and 15. Okay. So again, I'm going to look at this and see, is there a way I can get from 1 to 0 to 2 to 3 to 3 to 8 to 4 to 15. Of course, right now we're just looking only at the absolute value of these, not the sign. We'll take care of the sign here in a few minutes. Okay, so obviously I can't do anything right there. It doesn't appear to be. So let's, you know, add our extra row in there and think about what it is that we want to do here. If I multiply by 2, 2, 4, 6, 8, you know, 2 to 0, 4, if I just try what we did before, 2, 4, 6, 8, I can see that there still doesn't appear to be any relation from 2 to 0, 4 to 3, 6 to 8 at all. Okay, so let's take that back off. Okay, if I multiply by like 3, 3, 6, 9, 12, and again from 12 to 15, 9 to 8, 6 to 3, it just does not seem like nothing's working there. Okay, so what I'm going to suggest that we try now is try n squared. Okay, 1 squared is 1, 2 squared, 3 squared, 4 squared. And when we do that, we can see 1 minus 1. To get from 1 to 0, I subtract 1. To get from 4 to 3, I subtract 1. 9 to 8, I subtract 1. 16 to 15, I subtract 1. So we have taken care, by doing that right there, I can say that it's going to be n squared minus 1. Okay, now that takes care of the sign, or now we've got to take care of the sign. So by looking at the sign, we always want to do a -1 either to the n power or a -1 to the n. You can either do a plus or minus 1. Okay, I'd always do a plus 1. And the reason we pick a -1 is because, of course, 1 does not change the value of the answer. Okay, all we're trying to do is change the sign. So if I think about plugging in 0 here, you know, anything to the 0 power is 1. -1 to the first power would be a -1. A -1 squared would be a +1. A -1 cubed would be a -1. So that not -3, a -1. Okay, so that would be a positive, negative, positive, negative, positive, negative relationship. If I think about this one here, the n plus 1 power, 0 plus 1 would be, of course, 1, which would be a -1. Plug in 1, 1 plus 1 would be 2, a -1 squared would be 1, and that pattern would go on like this, would be a negative, positive, negative, positive, negative. Okay, so if you start with positive, negative, you want to just do the n. The negative positive is the n plus 1. So we have the positive negative relationship going, so we just want to do the negative 1 to the n power. You can either put it in the front or the back, it really doesn't matter. Normally it's in the front. And there's our expression right there. Anytime you're dealing with the positive negative relationships there back and forth, it's always going to have to deal with either this one here, the negative 1 to the n, or the negative 1 to the n plus 1. Okay, so now we're going to look at our next topic. It says a sequence can also be recursive, in the recursive form. A sequence in recursive form means that if you are given the first few terms, then you can determine all the other terms based on those preceding terms. And a very famous one is called Fibonacci. Mr. Fibonacci came up with a famous example using rabbits and how they reproduce and how fast they can do that. And if you click on that link in the iBook, you can see it'll take you to a website to explain all that. But we're going to look at the sequence that he developed there. Okay, it says the Fibonacci sequence is defined by the recursive function as follows: a sub 1 is 1, so the first term is 1, and the second term is 1. And the way you get the next term is you take those last two terms and add them together. Okay, and the k has to be, I should say, n, not k, but that should be an n right there. Okay, where n is greater than or equal to 2. So what we have is, we know the first term and the second term. Okay, and what we're going to do now is to get the third term. The third term is really the second term, the first term plus the second term. Okay, and the first term is 1, second term is 1, so 1 plus 1 is 2. The fourth term, if I plug in 4 there, 4 minus 2 is 2, a sub 2, 4 minus 1 is 3, so a sub 3. The second term is 1, the third term we just found out to be 2, so that 1 plus 2 is 3. A sub 5, if we have the a sub 5 would be the third term plus the fourth term, and the third term was 2, the fourth term was 3, so 2 plus 3 is 5. The sixth term is really the fourth term and the fifth term added together, which is just the last two. That is 3 plus 5, which is 8. And then the seventh term is the fifth term and the sixth term added together, which is really 5 and 8. 5 and 8, which is 13. So the sequence there is 1, 1, 2, 3, 5, 8, 13. That's a famous one called the Fibonacci sequence. The Fibonacci sequence dealt with adding previous terms to get the next term. There will be times in which you need to multiply. Last time we added things, okay? Now there'll be times that we need to multiply to get to the next term. A special type of this is called a factorial. A series of products of all the integers from 1 to n is called n factorial. So for example, 3 factorial really means 1 times 2 times 3, which of course is 6. 5 factorial means 1 times 2 times 3 times 4 times 5, which is 120. 10 factorial is 1 times 2 times 3 times 4 all the way up to times 10, which is 3,628,800. No, the only special case of this is 0 factorial. It's just kind of like anything to the 0 power is always 1. 0 factorial is 1. So let's look at this right here and try to figure out what these terms are going to be for this sequence here. Okay, so we have, let me change the color here to get a different color. We have 3 to the first power over 1 factorial. Of course, 3 to the first is just 3, and 1 factorial is just 1, so 3 over 1 is just 3. 3 squared over 2 factorial. 3 squared, 3 times 3 is 9. 2 factorial is 1 times 2, which is 2. You can write that as 9 halves or keep it as 4.5. Either way is fine. I'm just going to leave it as 9 halves. The third term, 3 cubed over 3 factorial. 3 cubed, 3 times 3 times 3 is 27. 3 factorial is 1 times 2 times 3, which is 6. Reduce that fractions by 3s to give us 9 halves. Squeeze it in there. Let me box these so they stick out. So of course we just keep this pattern going. 4 factorial. 3 to the 4th is 81. 4 factorial is 1 times 2 times 3 times 4, which is 24. And let's see, 81 over 24ths. Let me use my calculator real quick to reduce that fraction. It would be 27/8. Okay. And then we have 3 to the 5th over 5 factorial. 3 to the 5th is 243. And 5 factorial means 1 times 2 times 3 times 4 times 5, which is 120. And let me see if that will reduce at all. That reduces by 3, which goes to 81 over 40. And then wrap this thing up, 3 to the 6 over 6 factorial. I'm not sure what 3 to the 6 is. That's be 729. 6 factorial is 1 times 2 times 3 times 4 times 5 times 6, which is 720. 729 divided by 720, I would say that reduces to 81 over 80. Okay, so we have this new thing called factorial, and it can really make these patterns look really, really weird at this point. Okay, now we're doing example number 5, which is evaluating the expressions. So we have these expressions here. We're just going to try to simplify them down as far as we can. Okay, so let's look at 6 factorial divided by 2 factorial times 4 factorial. Remember, 6 factorial is just really 1 times 2 times 3 times 4 times 5 times 6. And 2 factorial is 1 times 2. 4 factorial is 1 times 2 times 3 times 4. Now what I want to do is see, is there anything I can reduce to make life a lot easier? Obviously 1, 2, 3, 4, 1, 2, 3, 4. These guys cancel out each other to 1s. And then I have the 1, 2, and 5 and 6, so the 2 can go into the 6 3 times. So what I have left up on top is 1 times 5 times 3, which is 15. And all I have left on the denominator is just 1, so it's 15 over 1, or just 15. Okay? Example B, or part B of that example, says 3 factorial, so that's, you can write it as 3, 2, 1, or 1, 2, 3. I normally just write 1 times 2 times 3, 1 times 2 times 3. You'll see me a lot of times start to leave off the 1s because the 1s really don't matter when you're multiplying, do they? I'll still write them there right now. So 1, 2, and 3, boom, boom, those are gone. 1 and 2, 1 and 2, they're gone. All we have left in the numerator is 3. The only thing in the denominator is 20, and that does not reduce any further. And there's your answer. Okay. X plus 1 factorial over x factorial. Now this one looks a little different. Remember, everything starts with 1 times 2 times 3 times 4 times all the way up until we get to whatever it is that we're looking at. X plus 1. So that really means like x minus 1 factorial times x factorial, because that's just the one right before x. This is x, and this is the one right after x, isn't it? I don't know why I put those factorial marks in there. It's not x factorial, it's just those. Let me get back to there. There we go. Times x plus 1. So all it's saying is you start with 1, go all the way, whatever x is, it can be whatever number. Get the number before that, the number, and the number after that, because that's where we want to stop. Okay? X factorial will just be, of course, 1 times 2 times 3 times 4 times all those until you just get to x minus 1 and then x. Okay? So as we can tell with everything else, 1, 2, 3, 4 all the way to x would cancel with all that denominator down there. So the only thing you'd have left is your x plus 1. So that weird looking thing just simplifies to that. Okay, so now we're going to look at the summations. There's going to be times that you're going to need to add up all those terms together. Okay? And we're going to look a whole lot more at summations in the next couple of sections with the geometric and arithmetic. But let me just tell you what this means and how this is written. Okay? Summation notation or sigma notation, this is the Greek letter sigma here. Okay? So you'll hear the word sigma a lot. Is a notation that is used for adding all the things up. The sigma means the sum of the stuff. Okay? So you'll normally see it written like this, okay? And what this is meaning is the bottom number down here tells you that's your, let's just go in order here, the index of summation. The variable using the expression is k. So it tells you right here that this letter right here is k, and that's k, okay? The upper limit of summation, the last number to substitute in the expression, okay, is your whatever it is up here. So let's say it's from 1 to 10. 10 would be the 10th term, would be your 10th term, and it would be a show of 10 right there. Okay. The lower limit, k equals 1 right here, that is showing you where you want to start on that. So let's make a lot more sense when we go over here and look at an example. So let's find the sum of each of these. Okay. So what we have, we're going to start at 1. We're going to go to 5 for 5k. Okay, so 5 times 1, 5 times 2, 5 times 3, 5 times 4, and 5 times 5. So what we do is just multiply those out. And then remember, the sigma means the sum, so we're going to add up all these guys. Get my calculator here. 5 plus 10 plus 15 plus 20 plus 25 will give you a total of, whoops, sorry about that, will give you a total of 75. And that's your sum of that sequence from 1 to 5. Okay, so that's here. Now it doesn't always start out with 1, sometimes it's going to start out with zeros, or whatever it is that you want to start. And the letters don't have to always be K, they can be K's, they can be I's, they can be whatever letters you want to use. A lot of times in these sections here, we're going to use I's and K's and N's. Okay, so let's look at 2i plus 1. So remember, it tells you to start at 0. So 2 times 0 plus 1, 2 times 1 plus 1, 2 times 2 plus 1, and 2 times 3 plus 1. 2 times 0 is 0, 1, that's 3, that's 5, 6, 7, so that's 10, and when you add up all those together, that would be a total of 16 for you. Okay, and the last one looks a little bit more complicated because it has a fraction and a factorial, but we go about it, just start going about it the same exact way as you've been doing all the others. So 5 over, remember, start with 0 factorial, 5 over 1 factorial, 5 over 2 factorial, 5 over 3 factorial, squeeze in down here, 5 over 4 factorial. Now remember, we said 0 factorial is always 1, so that is just 1. 1 factorial is 1 also, so that goes to 1. 2 factorial is 1 times 2, which is 2. 3 factorial is 1 times 2 times 3, and 4 factorial is 1 times 2 times 3 times 4, which is 24. When we add up all of those, let me get my handy dandy calculator here, because I don't want to try to do that in my head today. So when we do that, we're going to get a total of 325 over 24. That's going to be your exact answer. we always want to give exact answers with these. We do not want to round these things off and use a decimal. Now we're getting to the last one, finally. And we're going to talk about the finite series and an infinite series. It says when you find the sum of a finite or an infinite sequence, you're actually finding the series. That's what it's called. So a finite series is the sum of the first n terms of a sequence. Remember, finite stops, infinite goes on forever. This is also referred to as the nth partial sum and can be written as this. If you take the first term, second term, third term all the way, use the sigma notation, starts with I equals 1 and goes to whatever you want your last term to be of that expression there. Okay. Now an infinite series looks weird because an infinite doesn't stop at all, so it just keeps on going forever. And you wonder, how is it that we can find the sum of these? And we're going to talk about more of those in the next few sections. But you start with the first term, and since you go on forever, we go to infinity of that expression right there. So that's what these things are, how they're written. Let's look at an example now. The last example, number 7. It says, given the series k equals 1 to infinity of 4k plus 5 over k, find the fourth partial sum. So this is the series that keeps on going forever, okay? But we only want to find the fourth partial sum, meaning we want to look at 1, 2, 3, 4 only. We don't want to look at all of it. We just want to look at the first 4 terms. Okay? So I'm going to plug in 1, plug in 2, plug in 3, and plug in 4. So let's simplify these. 4, 9, 8, 13 halves, 12, 17 thirds, and 16 and 5 is 21 fourths. Now we are finding the fourth sum, so we're going to add up all those guys. And again, let me get my calculator out here. 17 thirds plus 21 fourths will give me a total of, again, do not give me a decimal answer because I want to know what it exactly is, 317 twelfths.